Welcome back to the Deep Dive. So today we're jumping headfirst into something that might sound a bit niche, but honestly the engineering behind it is pretty wild. We're talking high-end metal detectors, the really sophisticated tech people use to find history literally under our feet.
And our source material for this guide is, well, it's a really thorough technical review. This isn't your average user saying, hey, I found a coin. It's Paul Egerton's deep engineering analysis from February 2025. He looks really closely at 4 specific top-tier models: the XP-Des II, the Minelab CTX 3030, Minelab's Equinox 800, and the Garrett AT Max.
Okay.
And the key thing is he's not just looking at, finds, he's evaluating them on 11 critical engineering parameters.
Exactly. So that's our mission today. Put on those engineering goggles, try to understand why certain design choices matter, what they tell us about how these things actually perform out there, and what makes these high-tech machines different from a basic detector. Okay, let's unpack this.
Sounds good.
Starting with something the source really emphasizes right away: frequency range, and how these detectors actually use the electromagnetic spectrum.
Right. Think of frequency as maybe the detector's eyesight. Different frequencies sort of see underground targets differently.
Yeah.
Lower frequencies, say in the 1 to 10 kilohertz range, they're a bit like X-rays.
Right.
Really go deeper, penetrate further. They're generally better for larger objects buried way down, especially in mineralized soil, which can be, tricky.
But maybe not so great for the really small stuff near the top.
That's the trade-off, exactly. They can struggle with small, low conductivity targets close to the surface. Now, if you crank up the frequency, maybe 15 to 45 kilohertz, those act more like microscopes. Fantastic for spotting tiny things right under the coil, little gold flakes, thin old coins, small relics. But they tend to run out of steam depth-wise, especially if the ground conditions are tough.
So the source gives us the actual specs for these 4 detectors, how they handle frequency. The Minelab CTX 3030, it has this huge theoretical range listed 1 to 100 kilohertz across 28 distinct frequencies. That sounds incredibly versatile.
It does on paper offer a really wide potential spectrum. But here's where you see different engineering thinking. The XP-Des II, it focuses its operational range more tightly, kind of that 4 to 45 kilohertz sweet spot that covers a lot of typical hunting scenarios.
Right.
But, and this is key, within that range, it gives you 49 selectable frequencies. The source points out that's 75% more frequency granularity than the CTX 3030.
Granularity. Okay, why is having more specific frequencies to choose from, even in maybe a narrower overall band, such a big deal from an engineering standpoint?
It's absolutely crucial for dealing with electromagnetic interference, EMI. We're just swimming in electrical noise these days, right? Power lines, cell signals, Wi-Fi, even other metal detectors running nearby.
Yeah, definitely.
All that noise can really mess up your hunt. It can sound like false targets, or worse, it can mask faint signals from actual good targets. Having those 49 distinct frequencies lets you very precisely tune the detector to find a quiet channel to operate on. You can essentially sidestep specific noise sources.
Like finding a clear spot on the radio dial between all the static.
Exactly like that. It's a practical engineering fix for a really common problem. Now compare that to the Garrett AT Max. The source notes it runs on just one frequency, 13.6 kilohertz.
Just the one?
Just the one. So if you happen to be hunting somewhere with significant interference right at 13.6 kilohertz, well, your options for mitigating that noise are much more limited compared to the fine-tuning you can do with the Des II.
Okay, that makes sense. So that's about picking a frequency. But what about running multiple frequencies at the same time? The source says the Des II, the CTX 3030, and the Equinox 800 all do this. Yeah. And it's not just switching really fast, is it? It's something more advanced, like digital signal processing.
Oh yeah, this is where the tech gets really, really cool. Instead of just sending out one frequency pulse, waiting, listening, then sending another, these machines are transmitting multiple frequencies simultaneously. And they're analyzing the return signal not just for each frequency individually, but how the target responds across that whole spread of frequencies all at once.
And that tells you
more
about the target.
It tells you a whole lot more about what the target might be made of. See, different metals have unique conductivity signatures, and these signatures change depending on the frequency you hit them with. The source gives gold as an example. Tiny bits of gold might pop really well on higher frequencies, while a larger gold object might give a strong signal across a wider range. Iron, on the other hand, because of its properties, tends to show a more consistent response across different frequencies.
Mm.
So, by analyzing that simultaneous response pattern, the source called it the differential response, or the frequency-dependent conductivity signature. The detector's processor can make a much more educated guess about the target's identity in real time.
So it's like getting a multi-layered fingerprint of the target instantly without needing to manually cycle through frequencies or modes to figure it out.
That's a great way to put it, exactly. It leverages the underlying physics of how metals interact with different frequencies to give you sophisticated target ID on the fly.
Which leads us perfectly into discrimination, using all that info to decide if something's worth digging up. The source points out that these detectors actually have pretty fundamentally different ways of telling you what they think is down there.
Yeah, let's look at MineLab's CTX 3030 first with its Smart Find 2 system. Instead of just giving you a number, it displays discrimination information on a two-dimensional screen. It's like a color-coded map.
A map.
Sort of. It plots the target based on two properties. Its ferrous characteristic, how much iron it seems to have on one axis, and its conductivity, how well it conducts electricity, related to non-ferrous metals on the other axis. So a target shows up as a specific coordinate, a point on this grid.
Giving you a kind of visual profile of its metallic makeup. Interesting. How does the XP-DS2 sec handle discrimination?
The DSTS uses a more traditional numerical approach, but with some twists. It gives you an ID number, ranging from NACLIF 6.4 way up to 99. Plus, it has notch filtering, so you can tell it to ignore specific ranges of numbers, like common trash IDs.
Okay, wait, negative numbers. Negative 6.4. That seems odd for discrimination.
It does, right. But it's a very specific engineering choice highlighted in the source. Those negative values are designed specifically for dealing with highly mineralized ground.
Ah, the tricky soils again.
Exactly. In some soils, iron mineralization is so strong and gives off such complex signals that it can actually mask or hide the signals from good non-ferrous targets. That negative range represents specialized processing designed to help the detector differentiate between that difficult ground noise, confusing iron signals, and potentially valuable targets buried within that challenging matrix.
It's fascinating how much the specific environment, the ground itself, really drives these engineering decisions. The source also compares sensitivity ranges. The deuce the second goes from 1 to 99, but the Equinox 800 scale is 1 to 25. Why such a big difference? Is a wider range always better?
Not necessarily better in a simple sense, like it finds more things automatically. It's more about offering finer control. Sensitivity fundamentally is about adjusting the detector's amplification, trying to boost the signal from a target relative to the background noise.
Okay.
So cranking up the sensitivity makes the detector better at hearing faint signals from small or deep targets. That's good. But it also amplifies noise from the ground minerals, noise from electrical interference.
So a wider range, like 1 to 99, just gives you more steps, more precision in balancing that.
Precisely. If you're detecting in really hot ground, very mineralized, or near power lines, you'd need to back the sensitivity way down, maybe to 20 or 30 on the decimals the second, just to keep the machine stable and avoid constant false signals.
Right.
But if you move to, say, clean beach sand with very little mineralization or interference, you could push that sensitivity much higher, maybe 80, 85, even 90, to maximize your depth and your ability to hear those tiny targets without getting overwhelmed by noise. This raises an important question. How does the range impact performance in varied environments? Well, that wider range gives you more flexibility to optimize for whatever conditions you encounter.
And speaking of ground conditions, ground balancing is crucial. The source calls this fundamental electromagnetic theory in practice. All 4 detectors offer automatic and manual ground balance. But the tech behind it is pretty sophisticated, isn't it?
Oh, absolutely. Ground balancing is basically the detector trying to make the ground itself invisible, electromagnetically speaking.
Huh.
Soil isn't neutral. It contains minerals, often iron oxides, salts, things like that, which create their own electromagnetic response or signal.
Like background static drowning out the music.
That's a perfect analogy. The detector first measures this persistent ground signal. Then its internal circuitry generates an inverse signal, basically the opposite waveform, to cancel it out. It's very much like active noise cancellation in high-end headphones.
Wow.
By nullifying that overwhelming ground noise, the detector can then more easily hear the much fainter transient signal produced when the coil passes over a buried metallic target. Getting that ground balance right is absolutely critical for achieving good depth and maintaining stable operation, especially in difficult soils.
Okay, let's shift gears a bit. Wireless technology. The source compares how these detectors handle wireless communication, and it highlights some interesting engineering choices and trade-offs.
Yeah, this is an area where you see clear differences in design philosophy. The XPDS II really stands out here because it's, well, truly wireless. The search coil, the main control unit, and the headphones, they all talk to each other using a proprietary radio frequency link.
The big advantage being no cables.
Exactly. No cable connecting the coil to the control unit means nothing to get snagged on branches, nothing to potentially cause noise if it gets bumped or flexes. It's a big ergonomic win.
But the source mentions a potential downside, right?
Right.
Vulnerability to other radio interference.
Potentially, yes. Like any system using radio waves, it could theoretically be susceptible to interference from strong external RF sources. Now, the other detectors, they use more of a hybrid approach. The Garrett AT Max has its Z-Link wireless audio for headphones, and they claim it's 6 times faster than standard Bluetooth. They're really focusing on minimizing latency.
Okay.
MindLab does something similar with their Y-Stream tech on the CTX 3030, also for wireless audio, claiming latency below 10 milliseconds.
Latency, that's the delay between the coil detecting something and you actually hearing the beep in your headphones. Why is getting that delay down to milliseconds, like sub 10 meters, so important from an engineering viewpoint? Human reaction time is much slower than that.
It is. Human reaction is maybe 200, 300 milliseconds. But low latency in the detector matters directly for pinpointing accuracy. Sub 10 milliseconds feels instantaneous to us. If there was a noticeable delay, say even 50 milliseconds, you might physically sweep the coil past the target's exact location before your brain registers the audio signal.
So you'd overshoot.
Exactly, you'd overshoot, making it harder to know precisely where under the coil that target is located. Ultra-low latency ensures that the audio signal you hear is perfectly synchronized with the coil's physical position over the target at that exact moment. It makes pinpointing faster and more intuitive.
That makes a lot of sense. Let's switch to something maybe more physically obvious. Weight and ergonomics. The source compares the weights, and wow, there's a massive difference. The XPDS II comes in at just 2.2 pounds. The MindLab CTX 3030 is 5.2 pounds. That's more than double the weight. Shaving off 3 pounds is a serious engineering feat.
It absolutely is, and it points directly to some major advancements in materials engineering, lightweight composites, plastics, and significant component miniaturization inside the Deus II. 3 pounds might not sound like a huge amount if you just pick it up once.
Right.
But think about the actual use case. You're swinging that detector back and forth maybe thousands of times over several hours. Basic physics, right? Force equals mass times acceleration. That extra mass on the CTX translates directly into more biomechanical stress on your arm, your shoulder, your back.
So it's not just about carrying it in a spot, it's about how long you can actually hunt effectively once you get there.
Precisely. Cumulative fatigue is a real factor. It impacts your concentration, how accurately you swing the coil, your sweep speed. A significantly lighter machine, like the Deus II, allows for longer, less fatiguing, and therefore potentially more productive detecting sessions. It's applied physics optimizing the user experience.
The battery tech analysis in the source is also pretty revealing. It compares the coil battery life specifically. The XP Deus II coil gets around 20 hours, while the Equinox 800 coil gets about 12 hours. What does that kind of difference suggest about the underlying power management engineering?
It strongly suggests that the Deus II is likely using more power-efficient microprocessors and has really highly optimized algorithms for how it transmits and receives the electromagnetic signals. To get nearly double the runtime from the coil battery compared to the Equinox 800, especially while keeping the coil itself lightweight, points to some significant engineering wins in power efficiency.
And the Deus II also uses that distributed power system, right? Separate batteries in the coil, the control unit, and the headphones.
Yes, and what's interesting there from an engineering perspective is how that architecture can improve overall efficiency and add redundancy. Different components have wildly different power demands.
Makes sense.
The coil is the power hog. It's constantly transmitting strong electromagnetic pulses. The headphones sip power. By giving each major component its own dedicated optimized battery, you can better match the power source characteristics to the specific load. Plus, you get redundancy. If your headphone battery dies, the coil and controller keep working.
Okay, one last major spec comparison from the source. Waterproof ratings. This is where the material science seems to get really serious. There's a huge difference highlighted. The XPDS II is rated waterproof down to 66 feet. The other detectors compared are typically rated to 10 feet. The source stresses this isn't just about better seals, it's a fundamentally different pressure-resistant design philosophy.
It absolutely has to be. Going from 10 feet to 66 feet underwater is a massive leap in terms of the physics involved. At 66 feet deep, you're dealing with roughly 30 pounds per square inch, PSI, of additional water pressure pushing on every part of the detector compared to just below the surface.
Wow, okay.
That requires a whole different class of engineering. You need advanced polymer science for seals that won't fail under that pressure, incredibly robust housing materials that won't crush or deform, and maybe even internal pressure compensation systems. The source isn't exaggerating when it compares it to submarine-grade engineering. What's fascinating here is seeing those kinds of extreme, almost industrial-level engineering principles applied to what's ultimately a consumer device.
Okay, so we've gone through frequency tech, discrimination, wireless, weight, power, waterproofing. Pulling all that technical detail together from the source, what's the overall engineering takeaway from Paul Edgerton's comparative review?
Well, based strictly on the objective engineering specifications that he analyzed and compared, the source concludes that the XP days the second demonstrates, frankly, superior engineering across multiple critical parameters. Specifically, its frequency granularity for handling noise, its really remarkable weight optimization, the efficiency of its power management system, that extreme waterproof capability, and its fully integrated wireless design.
And this seems like a really important, but the source immediately adds that crucial piece of nuance, right? That the best detector isn't necessarily the one that ticks the most engineering boxes on paper. It really depends heavily on your specific needs, your specific application.
Absolutely, 100%. Someone whose primary goal is hunting for deep, old relics in really challenging soil might find the theoretical depth advantage of the CTX 3030's broad frequency range more beneficial, despite the weight.
Okay.
Or someone else might prioritize battlefield-level ruggedness and straightforward operation, maybe finding the Garrett AT Max's relative simplicity appealing.
So the key engineering insight isn't just this one is technically superior overall, but maybe more, that each of these manufacturers has made very deliberate engineering choices. They've optimized their designs differently, maybe for different target users, different hunting styles, accepting different trade-offs. The Days de Sireka looks like the current peak of integrating a lot of advanced tech into one lightweight package, but it's still just one specific engineering approach among several valid ones.
Well said. And the source drives home one final, absolutely critical point that really connects everything. No matter how sophisticated the detector's technology is, its actual performance out in the field relies massively on the skill and understanding of the person using it, and of course on the specific environmental conditions of the day.
That feels intuitively right. You could have the most advanced feature-packed machine in the world, but if you don't grasp how ground minerals are affecting the signals, or how to properly interpret the discrimination feedback, or even just how to maintain a consistent, effective coil swing, you're just not going to get the best out of it. The tech is an incredibly sophisticated tool, but its effectiveness is fundamentally tied to the user's knowledge and skill.
Exactly. These aren't simple beepers anymore. They're complex electromagnetic measurement instruments. To truly master one requires a technical understanding not just of the machine itself, but also of the physics of the environment, the ground, the interference, the targets. It really is about matching the right technology to the application and to the user's level of expertise. And for any of you listening who want to really dig into the weeds on these specs, the detailed numbers and Paul Edgerton's full comparative breakdown, we'll definitely put a link to his original review in the description. It provides some genuinely valuable engineering insights if you're into that level of detail.
Yeah, definitely check that out. What a fascinating deep dive, though. We've touched on everything from how radio frequencies find stuff underground to how these machines try to guess what they've found, how wireless signals affect your pinpointing, and even how something as basic as weight, just pure physics, impacts how long you can effectively search. So what does this all boil down to? Well, here's maybe a provocative thought to leave you with. Given how much the ultimate success finding that target seems to depend on the operator's understanding, their ability to calibrate the machine correctly, their skill in working with both the technology and the environment, does the person holding the detector effectively become the final, most critical piece of engineering in that whole metal detection system? Something to think about.
Thanks for joining us on this deep dive. We hope it gives you maybe a new appreciation for the incredible applied physics and clever engineering that can be hiding in objects all around us, even the ones used to search for history right beneath their feet.